Are you happy with your life? This question, which at first glance may seem simple, forces us to think beyond the everyday and confront the unknown. In the vast universe, there is a mystery as intriguing as the doubts we have about our own existence. Dark matter, invisible and mysterious, it makes up most of the cosmos, exerting a decisive influence on the formation and dynamics of galaxies. And, even though it is fundamental to the functioning of the universe, no one knows exactly what it is. How can something so crucial be, at the same time, so deeply unknown? Dark matter holds galaxies together, acting like a gravitational glue that prevents normal matter from dispersing. It influences everything around us, but remains hidden, detectable only through its effects on visible matter. On this journey, we will delve into this enigma, understand what dark matter is, investigate why it is so difficult to detect, and explore the substance's vast implications for physics, cosmology, and our understanding of the universe. The story of dark matter begins with observations of the visible universe. At the beginning of the 20th century, as astronomers studied galaxies, an awareness began to emerge that something didn't quite fit together. The galaxies showed movements that could not be explained solely by the gravity of the stars, gas and dust that were visible to our instruments. It was Fritz Zwicky, a Swiss astrophysicist, who first suggested this discrepancy when studying the Coma Galaxy cluster. Zwicky realized that the observed mass was insufficient to hold the galaxies together under gravitational action. He concluded that there must be a much larger amount of mass, a mass that did not emit light, which he called Dunkel Materie, or dark matter. At the time, Zwicky's ideas were met with skepticism. Cosmology was still in its infancy, and the notion that an invisible substance could dominate the dynamics of galactic clusters seemed absurd. However, their observations put to rest any doubts. The visible mass was simply not enough to explain the orbital movements within the cluster. Decades later, in the 1970s, astronomer Vera Rubin, in partnership with Kent Ford, carried out a crucial study of spiral galaxies. Using high-precision spectroscopy, Rubin measured the velocities of stars in different regions of galaxies. Surprisingly, she found that stars at the edges of galaxies moved at almost the same speed as stars in the center. According to the laws of physics formulated based on visible matter, more distant stars should be less fast, given that the gravitational force would decrease with increasing distance. This finding indicated that there was an additional, invisible mass that provided the traction necessary to maintain the movement of the stars. The discovery of the uniform rotation curves of galaxies reinforced the idea that visible matter represents only a small fraction of the total mass of the universe. Current estimates indicate that only 5% of the universe is made up of baryonic matter, while approximately 27% is dark matter, and the remaining 68% is dark energy. Dark matter, although we cannot see or detect it with traditional methods, exerts an intense gravitational influence, being essential for the formation and evolution of cosmic structures. But the question arises, what exactly is this dark matter? The answer remains evasive. One of the most accepted hypotheses suggests that it is composed of exotic subatomic particles, called WIMPs, weakly interacting massive particles. These particles would have enough mass to generate the observed gravitational effects, but their interaction with normal matter would be so weak that they escape detection in current experiments. Another hypothesis argues that dark matter is formed by MACHOs, massive compact halo objects, such as black holes, brown dwarf stars, or wandering planets, which do not emit light and, therefore, go unnoticed. However, although this explanation is partly viable, it is not sufficient to explain all observed gravitational phenomena. The real difficulty in detecting dark matter lies in its nature. It does not emit, absorb, or reflect light, thus being invisible to our conventional telescopes. Its presence can only be inferred indirectly through the gravitational effects it causes on the movements of stars and galaxies. In search of lengths of this mysterious substance, scientists have been developing increasingly sophisticated experiments. Underground detectors, such as the LUX-ZEPLIN experiment, are installed in environments highly protected from cosmic radiation in order to capture the very rare interaction between dark matter particles and atoms of ordinary matter. These experiments, although intensive and expensive, have established important limits on the properties of dark matter particles. Other efforts use particle accelerators, most notably the Large Hadron Collider, LHC, which operates on the border between Switzerland and France. In this gigantic laboratory, particles are collided with extreme energies to try to recreate the conditions of the beginning of the universe, enabling the formation of exotic particles that are candidates for making up dark matter. Although the LHC has not yet produced a direct detection, it has contributed significantly to refining our theories, opening new hypotheses, and directing future experiments. Additionally, advanced space telescopes, such as the James Webb Space Telescope, are being used to pick up indirect signals from dark matter, observing how its presence affects light from distant galaxies through gravitational lensing techniques. From these observations, astronomers have mapped the distribution of dark matter on cosmic scales and reconstructed the famous cosmic web, in which dark matter forms filaments that connect clusters of galaxies. Dark matter is essential for understanding the universe. Without this invisible mass, the formation of galaxies, according to current observations, would be impossible. Baryonic matter, which makes up the stars and planets we see, would not be capable of generating the gravitational wells necessary to bring matter together into large structures on its own. In other words, dark matter acts as an invisible structure or glue that holds the entire universe together. Furthermore, observed discrepancies in the rotation of galaxies and other cosmic phenomena suggest that Einstein's theory of general relativity may not be sufficient to explain all gravitational interactions, leading some scientists to consider alternatives. Modified Newtonian dynamics (MOND) is one such attempt to tweak the laws of gravity without resorting to dark matter. But most cosmologists still see dark matter as the most robust explanation for the observations. Furthermore, dark matter is closely linked to dark energy, a mysterious force that accelerates the expansion of the universe. Together, these two components represent about 95% of the composition of the universe, challenging our most basic concepts about the nature of reality. Understanding how these two elements interact and influence the formation of galaxies is fundamental to predicting the fate of the universe and consolidating a coherent cosmological model. The importance of dark matter transcends the limits of cosmology and extends to particle physics. The challenge of detecting these weak, invisible particles is shaking up the scientific field, forcing researchers to rethink fundamental theories. If one day we can truly understand the nature of dark matter, we can eventually unify general relativity with quantum mechanics, two of the greatest and most formidable theories in physics, but which currently do not fit together perfectly. The search for dark matter has driven a series of technological innovations and deepened collaboration between scientists from different countries and specialties. Underground detectors such as LUX-ZEPLIN and XENON-1T, installed in isolated locations to reduce interference, have been fundamental in trying to capture rare interactions between dark matter particles and baryonic matter atoms. These experiments set important limits and help shape future research. At the same time, the Large Hadron Collider (LHC) has been used to collide particles at very high energies, in the hope that new exotic particles candidates for dark matter can be revealed in the environment of extreme conditions. Although direct detection using the LHC has not yet occurred, the data extracted has significantly expanded our understanding of fundamental forces and contributed to the improvement of theoretical models. In addition to terrestrial experiments, astronomy has also played a fundamental role. State-of-the-art telescopes, such as the James Webb Space Telescope, have allowed the observation of phenomena at previously unexplored wavelengths. Using the gravitational lensing technique, which uses the bending of light caused by large masses to map dark matter, scientists were able to visualize the distribution of this substance in the universe and thus confirm its importance in the formation of the cosmic web. International collaboration is one of the pillars of this search. Projects like the Dark Energy Survey bring together scientists from different countries to map dark matter and dark energy, sharing data and theories that accelerate the advancement of knowledge. This collaborative network is essential to overcome the complex challenges that dark matter presents and to develop the new technologies that can enable its detection. Despite countless advances, dark matter remains a huge enigma. One of the biggest challenges is its direct detection, which, to date, has not yet been achieved. Despite billion-dollar investments in high-technology experiments, this limitation has provoked intense controversy in the scientific community, with debates about whether we are really on the right track or whether perhaps we need to rethink fundamental aspects of our theories, such as the laws of gravity. Some proposals, such as modified Newtonian dynamics, MOND, suggest that the observed discrepancies can be explained without the need for dark matter. But most scientists argue that dark matter is, in fact, the best model to explain the observations. Another dimension of the challenges involves ethical and financial issues. The immense cost of detection experiments and discussions about resource allocation in science raise concerns about whether investments could be better targeted at more immediate problems. There are also debates about intellectual property and data sharing, with the increasing need for collaborative and transparent policies, so that science can advance in a global and integrated way. These challenges and debates have implications that go beyond physics. The search for dark matter provokes deep reflections on the nature of reality. If most of the universe is made up of something that can't be seen, what does that say about visible matter? Are perceptions based solely on light, in fact, a small part of a much larger picture? These questions not only challenge science, but also touch on central philosophical questions about knowledge and existence. Dark matter forces us to rethink the foundations of what we consider real and to embrace the unknown. Each advancement and each new technology that allows us to investigate these cosmic shadows is a step towards a deeper understanding of the universe and, by extension, ourselves. This incessant search for the unknown is what defines our humanity and our desire to surpass the limits of knowledge. The future understanding of dark matter could trigger a true revolution in the field of physics and also in practical technologies. If one day we are able to understand and even manipulate this substance, we could develop energy sources based on dark matter, create revolutionary materials, and transform entire industries. Imagine a future where energy derived from dark matter is clean and practically unlimited, contributing decisively to climate change mitigation and space exploration. Furthermore, understanding dark matter could guide the search for extraterrestrial life. If dark matter influences the formation of galaxies and stellar systems, then its study could help identify regions of the universe that are most likely to harbor life. These discoveries would guide future space missions and elevate our understanding of the possibility of life on other planets, transforming not only astronomy but also our place in this vast cosmos. In-depth investigations into dark matter also contribute to technological advancement in several areas. The detectors and methods developed for this research have applications in medicine, security, and other areas of science. Particle detection technology, for example, has the potential to enhance medical imaging techniques and improve security systems, an unexpected benefit that arises from researching one of the universe's greatest mysteries. The influence of dark matter also extends to the cultural field. Its discovery and the evolution of our understanding of it can inspire new forms of artistic expression, philosophical debates, and literary narratives that reevaluate our understanding of the universe. By challenging our perceptions of reality, dark matter can lead to innovations that transcend the traditional boundaries of the arts. The journey to uncover dark matter is a true testament to human curiosity and persistence. From Fritz Zwicky's first observations, through Vera Rubin's revolutionary discoveries, to modern underground experiments and international collaborations, each step of this scientific adventure has expanded the boundaries of knowledge. Dark matter, invisible but fundamental, has already transformed the way we understand the universe, forcing us to recognize that what we see is just a fraction of a much larger and more complex picture. Dark matter research has driven technological innovations, opened new partnerships, and constantly challenges our theories about the nature of gravity and matter. Despite challenges and controversies, from the difficulty of its direct detection to ethical debates over resource allocation, the search for dark matter continues. Fueled by the awe we feel for the unknown and the inexhaustible desire to explore the limits of the universe, every experiment and every supercomputer simulation brings us a little closer to the secrets that lurk in the cosmic shadows. By observing how dark matter influences the rotation of galaxies and the formation of massive structures like the cosmic web, we expand our understanding not only of physics, but of existence itself. This collective effort, uniting scientists from different parts of the world, illustrates that the search for knowledge is a global endeavor, an effort that transcends borders and constantly reinvents itself to better explain the universe. As we move towards a possible understanding of dark matter, questions arise that intertwine with the limits of our understanding. If dark matter makes up the majority of the universe, is what we perceive through our senses just a small part of reality? Could it be that there are hidden dimensions, parallel universes, or fundamental forces not yet understood that manifest themselves through this invisible substance? All these questions challenge us to rethink the concepts of time, space, and even consciousness itself. The hypothesis that dark matter could be the indispensable piece to unify general relativity with quantum mechanics leads us to imagine a future where our fundamental theories are integrated into a single cohesive explanation for the forces of the universe. Such an advance would be comparable to the quantum revolution of the 20th century, transforming our ability to explore and, perhaps, even manipulate natural forces. In practical terms, understanding dark matter could pave the way for revolutionary technological innovations. Imagine clean energy sources generated from properties that we currently only infer, or materials with very light and resistant characteristics, capable of transforming sectors such as computing and space exploration. The impact of such discoveries would be immense, not only renewing our global economy, but also providing essential tools to address critical environmental challenges such as climate change. The discovery could also boost our search for extraterrestrial life. If dark matter is crucial in the structural formation of the universe, understanding its distribution can indicate which regions of the cosmos are most conducive to the emergence of life. This information would not only guide future space missions, but also redefine our perspective on the prevalence of life in the universe, challenging the notion that Earth is a singular case. Dark matter, as an invisible but essential substance, forces us to question not only the laws of physics, but our own concepts of reality. If most of the universe is made up of something we cannot see, how does this change our view of visible matter, life, and the meaning of existence? This reflection transcends science, delving into the field of philosophy and art. Artists, writers, and filmmakers are already inspired by this idea to create works that explore the unknown and the invisible, giving new meaning to our understanding of the world. The possibility that hidden dimensions or parallel universes are linked to dark matter broadens our field of investigation, suggesting that what we perceive is just the surface of a much richer and more complex reality. This perspective invites us to a constant state of questioning and searching, where each answer discovered opens doors to new questions. It is this eternity of inquiry that defines the essence of science and human curiosity. 2. Solve the mystery of dark matter. The scientific community has joined forces in an unprecedented way. International initiatives, such as the Dark Energy Survey, bring together astronomers and physicists from different countries to map, on a large scale, the distribution of dark matter and dark energy, using advanced telescopes and innovative techniques. This global collaboration is remarkable and symbolizes a collective effort to transcend the limitations of current technology. At the same time, the use of new tools, such as artificial intelligence and machine learning, has accelerated the analysis of immense sets of astronomical data. These emerging technologies are helping to identify subtle patterns that could be indirect signs of dark matter, improving our ability to detect it and understand its effects. Experiments in underground detectors and particle accelerators have contributed significantly to our understanding. Each limit established, each new hypothesis tested, consolidates dark matter as a vital piece of the standard cosmological model, responsible not only for the formation of galaxies, but also for the ultimate fate of the universe. The exploration of dark matter is, above all, a testament to human beings' innate curiosity. This never-ending quest for the unknown is not just about unraveling a scientific mystery. It is also a reflection of our own essence, of the desire to understand the cosmos and find our place within it. Each advance in this area, from Zwicky's first observations to modern LHC experiments, brings us a little closer to the truth. Even if that truth is hidden in the shadows of the universe, dark matter challenges the traditional perception of reality, reminding us that what we see is only a small part of what actually exists. It urges us to imagine new dimensions, to consider the possibility of parallel universes, and to question whether our understanding of physics is, in fact, complete. This line of thinking inspires us to keep asking, exploring, and innovating. Furthermore, dark matter has the potential to revolutionize not only physics, but also technology and our cultural worldview. If we can one day manipulate it or understand it more deeply, it could lead to innovations that transform entire industries, from energy to the development of advanced materials, and even the way we explore space. Culturally, the revelation of the secrets of dark matter could inspire new artistic, philosophical, and literary expressions. By challenging our perception of reality, it opens space for a new reinterpretation of our narratives about existence, which can give new meaning to our relationship with the cosmos. We can reimagine art and literature in ways that embody this new vision of the universe, producing works that question the very nature of the visible and the invisible. If dark matter makes up most of the universe, is our world really what it appears to be? This question leads us to reconsider everything we think we know about reality. Could there be hidden forces and dimensions, hidden in the shadows of the cosmos, that we cannot yet imagine? If dark matter is, in fact, a portal to the unknown, our view of space and time, concepts we consider fundamental, would be radically transformed. Thinking of dark matter as a portal to additional dimensions forces us to confront the possibility of a universe far more complex than we can understand. If we could interact with these hidden dimensions, revolutionary technologies and knowledge could emerge, reshaping our understanding of physics, the passage of time, and human consciousness itself. What about life? If dark matter is crucial to the formation of galaxies, what role does it play in creating habitable worlds? Can its influence be decisive in the origin of life, on scales and forms that we have not yet mastered? If dark matter is found to be somehow intertwined with the very essence of life, this discovery would transform our search for civilizations beyond Earth, and potentially reveal that life is more common in the universe than we ever imagined. Dark matter also challenges our very existence. If most of the universe consists of something invisible and enigmatic, how does this affect our perception of reality? Are we prepared to accept that what we see is just a fraction, perhaps insignificant, of a much bigger picture? This realization, which shakes our beliefs about meaning and purpose, calls us to embrace the unknown, to continually expand the limits of our understanding. Facing dark matter means, above all, accepting that the search for knowledge is infinite. Each new discovery opens the door to additional questions and reveals aspects of the universe that previously went unnoticed. Dark matter challenges us to continue exploring, to keep the flame of curiosity alive, and to understand that the path to knowledge is full of surprising discoveries, even in what today seems impossible. As we look to the future, we must ask, what new revelations await us in the shadows of the cosmos? Are we prepared for the profound implications that will come when we finally understand dark matter? The journey to unravel this mystery is an ongoing adventure, an exploration of the frontiers of human knowledge that will continue to inspire and challenge generations. This relentless search defines our humanity and keeps alive the hope of unlocking the most intricate secrets of the universe. If the nature of dark matter is finally revealed, the implications will be revolutionary. Understanding it could transform fundamental physics, uniting general relativity and quantum mechanics into a cohesive and comprehensive theory. This advance would not only change the way we see the universe, but would also pave the way for technologies that we can only imagine today. Clean energy sources based on dark matter, materials with incredible properties, and even new forms of space exploration that would allow more efficient interstellar travel. The discovery of dark matter could also guide our search for extraterrestrial life. If this substance influences the formation of galaxies and stellar systems, understanding its existence may indicate which regions of the cosmos are most favorable to the emergence of life. This information would be essential for future space missions and for identifying exoplanets that could host living organisms, revealing that the occurrence of life may be much more common than previously thought. In addition to its direct impacts on science and technology, dark matter has the potential to transform our cultural and philosophical approach to the universe by forcing us to rethink the foundations of our understanding of reality. It invites us to develop new narratives in art, literature, and philosophy that give new meaning to our place in a vast and enigmatic cosmos. This shift in perspective could lead to a cultural renaissance, where the human imagination is encouraged to explore beyond the limits of the visible, opening up new cognitive and emotional frontiers. Global participation in dark matter research through international collaborations and interdisciplinary projects is an example of the human spirit in the pursuit of the unknown. Scientists from different areas, using advanced technologies and new analysis methods, are together trying to uncover the secrets of this invisible component of the universe. This collaboration not only accelerates the progress of science, but also symbolizes humanity's collective commitment to pushing the limits of knowledge. In short, dark matter is much more than a scientific enigma. It is an invitation to rethink our view of reality and to embrace the complexity of the universe. She challenges us to grow, to innovate, and to keep asking, even when the answers seem so elusive. Each breakthrough, however small, is a reminder that the unknown drives us to keep pushing against the limits of our understanding and creativity. As we continue on this unfinished journey of discovery, dark matter remains a beacon that guides us beyond what our eyes can see. She reminds us that the universe is a vast field of possibilities, where the invisible can be as determining as what is visible, and where the search for knowledge is as infinite as the stars. Thus, dark matter remains one of the greatest mysteries of modern physics, a symbol of our constant desire to explore the depths of the cosmos, and by extension, ourselves. Each new hypothesis, each experiment carried out to detect it, and each technological advance that goes beyond the limits of what we know, reinforces our commitment to the idea that understanding the universe is a never-ending adventure. Even though dark matter remains hidden today, its influence has already fundamentally altered our view of the cosmos, and will continue to inspire future generations of researchers. innovators, and dreamers. All of us who want to understand our place in a universe full of mysteries, possibilities, and infinite horizons.